We now consider an optimization problem where we're given a surface defined by f of xy as x minus 10 plus a circular type value x squared plus y squared over 20. And unlike our earlier examples where we would simply look for the optimum values of this function by itself, we're going to limit ourselves to values of x and y that satisfy x plus y equals 10. Now this kind of constraint is classically called a budget constraint because it shows up whenever you're doing budget type calculations and limits on budgets, because what we're saying here is, or we can interpret it as, if we have cost 1 and we have cost 2, then those must add up to 10 at a maximum. So whenever we have this sum of our two inputs must equal some value, we can think of it as how do I trade off where I'm going to spend my money to maximize some output. There's also a graphical interpretation of this, and if we look at the x plus y equals 10, we can rearrange that to be y equals 10 minus x. And so any constraint of this style, one input plus another input equals a fixed value, then we get a nice straight line constraint, like so. And this is the graph of y equals 10 minus x. Our axes are x and y, and 10 is the intercept. Slope is -1, so we'd have values like that. So if you're trying to imagine the geometric version of this, we have x and y, and there's a surface over top that we can't see, but it's being defined by this function here. And what we're allowed to do is walk along this path, this road here, and we can imagine going uphill and then downhill, and then maybe uphill again, downhill. Somewhere along that path should be some local maxima or possibly minima if we consider only the points on that line. That's what we're studying now. Our first step when we're trying to analyze this and use algebra to identify the max and min points is to look at the equations we need. So the first two are that we have f sub x equals lambda g sub x, f sub y, so the y derivative is lambda g sub y, and g of xy equals k. Now, what are those in the context of our problem here? Our problem had a function, so that's pretty clear, but nothing was labeled g when we started. So what we have to do is infer or interpret what we had there. X plus y equals 10. That can be thought of or written as g of xy equals some constant k, and that's where we derive this new function g. We can think of x plus y equals 10 being a line, or we can think of it as being one contour among many lines, and that's how we choose to interpret it when we're talking about Lagrange multipliers. We've got g of xy as being the x plus y. We can use that on the next page. So if we have our function, which was, pause, x minus 10y plus the x squared y squared over 20, and g is simply x plus y. Now we can fill in these values here. The x derivative would be 1, let's stick with blue. The x derivative would be 1 plus 2x over 20. That is our x derivative of f. And at the optimum only, that's going to be equal to some unknown value lambda times the x derivative of g, which is just 1. gx. And then we can do the same thing for the y derivative of f, which would be -10 plus y squared's derivatives, that's 2y over 20, equals lambda times the y derivative of g, which is just 1. There we go. And the last, or third equation comes from the constraint. Oh right, x plus y must equal 10. That was given to us straight up. So again, we have 3 equations and 3 unknowns. Our goal in particular is to solve for the x and y's that satisfy these, and maybe later on we might be interested in lambda, but x and y are really our focus. Lambda's, for now, just an element that we need to talk about, the optimum point being where the gradients are parallel and not necessarily equal to each other. Okay, 3 unknowns. In fact, if lambda is the one we want or are least interested in, we might as well solve for it. In fact, we have lambda here and lambda here. We can actually set equation 1 and equation 2 equal to each other because they're both equal to lambda. And that gives us an equation of 1 plus 2x over 20, or just x over 10, is equal to the other half minus 10 plus y over 10. And if we sort that around a little bit, we can get 11 equals y over 10 minus x over 10. And that gives us a relationship between x and y. We can also use this third equation to solve maybe for y in terms of x. So the third equation gives us y equals 10 minus x. And that can be inserted into this other equation, and we can eliminate y. It's important to note that you can solve these equations however you like. There are often different routes you can pursue. As long as you get down to x equals and y equals, we're happy. This seems like the most straightforward route for this particular problem, though. So we have y equals, we can sub that in, so 11 equals something over 10 minus x over 10, and that something is 10 minus x. And if we continue with that a bit further, we can get, so we can expand that out. We have 11 equals 1 minus x over 10 minus x over 10, or that's better known as 2x over 10, or x over 5. So 11 equals 1 minus x over 5, and so 10 equals minus x over 5, careful with the signs, and that gives us x equals negative 50. Perfect. So when we look to satisfy all 3 of these equations, which are required to find the optimum values of f under the constraint here, we end up with x equals negative 50, and if we combine that with 3, let's call that 4 for a second, 4 being subbed into 3, we get that the y value is going to be 10 minus 50, and that will be 60 equals y. So those 2 x and y values will solve or satisfy our equation. So actually we got ahead of ourselves there. We have solved these equations. What does it mean and how do we interpret it? Well, there's only one point that we found. So on this line, y equals 10 minus x, or x plus y equals 10. We found one point at x equals negative 50, so out here somewhere, and y equals 60. Let's go a little bit higher here. There we go. So 60, not quite to scale. That is the only point that satisfied our equations. And what we can do is evaluate the function there. F at negative 50, 60 is equal to, remember our function was x, so minus 50, minus 10y, minus 10 times 60, and plus x squared plus y squared over 20. And now we have x and we have y. Our x is negative 50, our y is 60, and there we go. Negative 345. Okay, so what does that tell us? It tells us that the surface height at this point here, x, y, gives us a z, or a height, of negative 345, so well below the plane here. We can imagine it going down into the page. That is tough to compare with. Just to get a comparison, though, at some other point, let's say relative to the value at 0, 10 would be another point on this graph. If x was 0, y would be 10, the function value at 0, 10 is minus 95. And so if we compare points here, let's put another one on here. This one has f equals minus 95. This one has f equals minus 345. So it would appear, just by a quick comparison, that this point is likely a minimum of the function if we're limiting ourselves to this pathway, to this line y equals 10 minus x. And it's hard to confirm that. It's hard to actually come up with a good proof for that. I think the easiest argument that it's actually a minimum for minus 50, 60 being a minimum on the constraint is that it's the only point found, only min-max point found, and as x and y increase along the constraint y equals 10 minus x. So in other words, as we move out along this line here, the term that's going to dominate the calculation is going to be the quadratic term. We're going to have x squared plus y squared. Even if they're negative, they're going to be squared, so they all become positive. This term is going to get positive, and it's going to get bigger and bigger. And the squared terms are going to be much bigger than the linear terms when x and y are large, and so we can say that as x and y increase along this, the function value is going to go towards positive infinity. And so if we found one point that's special and it goes up towards infinity in either direction, that's pretty much our evidence. The point at minus 50, 60 must be a local min on the constraint. Now notice this is not the same second derivative test. We can't use any of the rules we saw earlier simply because we're not free to choose which direction we go in. It's not an issue whether the function goes down somewhere else because we can only walk along this pathway. So it's a different problem with different techniques, and one of the challenges is that identifying or uniquely making a case that something's a local min or max is more challenging here. Secondary note, there would be no maximum point on the constraint for exactly the same logic we just went through. We only found one potential point, and it was here, and it was very, very low, and we know the function goes up if we move along the path away from there, so there cannot be a maximum on this constraint. Last but not least, we'd like to tie this back into our graphical ideas. So here, these red lines are the contours of f. And notice the scaling here, we're around minus 40, minus 50, and we see our straight line here, which is our constraint line, sorry, contours of f, and this is our constraint line, x plus y equals 10. And if we zoom in on this region here, look what we can see. At minus 50, we have our constraint line just coming along to touch, our minus 345 function value. And what else do we see there? But we see our straight line. If we were looking for a gradient, it would be going upwards. So this direction here would be the gradient of f, pointing uphill and perpendicular to the red lines. And we don't exactly know which direction the other contours go in, but in some sense, a line perpendicular to the black line would be parallel. And that would be our gradient of g, which is the gradient of our x plus y function, our constraint g of x here. G of xy, sorry. So this is the graphical picture where now we can imagine the surface is at a minimum and heads up and up and up as we go in this direction here, but we're not allowed to do that. So if we wanted to go downhill, we'd head this direction. But if we're walking along this pathway only, we can see, okay, we're going downhill, just not as quickly as we could if we went off path. But as we go down this hill, we eventually reach a minimum, and then we're going to go back up towards following these higher contours if we keep following that path. So it's a much more intricate picture that we're trying to draw here. The key element for us right now is this idea that when we reach some special point, maximum or minimum, we're going to have this condition satisfied that the gradient of our function and the gradient of our constraint function are going to be parallel to each other, which is our starting point in the algebra.